So this reaction can actually be thought of as a contest between the zinc and the copper ions for 2 electrons. And the question is, which one wins? Now, we know the answer because I've actually showed you the pictures, but how would you know that in general? So why is it that zinc metal reacting with copper gives you zinc plus 2 and copper, but the reverse one will not give you anything? If you take a piece of copper metal and put it in a zinc solution, you do not observe the formation of copper plus 2 and zinc. So could you predict that without having to do the cumbersome experiment? And the answer is sure, and this is what a table of standard reduction potentials is for. They look like this. So this is reproduced from the appendix of a generic Gen Chem textbook. Your actual book or ebook will have something pretty much just like it. And it is just a list of reduction reactions and the potential for that half reaction. You'll note these are half reactions. They all explicitly mention electrons, and they are all in the product. And this one right here is often used as a reference point. The oxidation of protons to form hydrogen atoms, or actually hydrogen gas, is said to be 0. Many of them have are potentials that are more positive than that, and many have them that are more negative than that. So what do these mean? And I'm going to focus in on the 2 reduction half reactions that have to do with the copper zinc example that we just talked about. All right, so I'm just going to bring those 2. So these are these 2. So the standard reduction potential of copper plus 2 to form copper is said to be positive 0.34 volts. And the standard reduction potential of zinc plus 2 to form zinc metal is negative 0.76 volts. So what this means, when you compare these numbers, the one that is the more positive one is the one that it's called the stronger reducing agent, and that is the reaction that is more likely to happen, which is to say that if copper plus 2 and zinc plus 2 are competing for 2 electrons, copper plus 2 is going to win because it has the more positive reduction potential. What does it mean for standard reduction potential? So the standard means the same thing that it has meant for the past year, which is that basically we're talking about 1 molar copper or 1 molar zinc in this case. So to use some vocabulary that we got from the first, way back in the first video, the fact that this has a more positive reduction potential tells you that copper is a better oxidizing agent than zinc is. And as such, that's what's going to happen. And the reverse of this happens. So this is actually why there's no need for a subsequent table of standard oxidation potentials. This just tells you that the reverse of this process will occur, and if you reverse the reaction, the potential for that process, which now becomes the oxidation potential, will be the opposite of this. So let's do that. And basically, to get the standard cell potential, just add the reduction and the oxidation potential. So for the example, we know that the copper plus 2 is going to stay as is. That's going to be the reduction half reaction that occurs at the cathode. So that's going to contribute positive 0.34 volts. The zinc will be reversed to form the oxidation half reaction, zinc metal, becoming zinc plus 2 and 2 electrons. So then this is the oxidation potential at the anode, which is now going to be a positive 0.76 volts. Remember, you have to flip the reaction, flip the sign on the potential, add everything together. the electrons should cancel. And you get copper plus zinc gives you copper plus 2 plus zinc metal gives you copper metal plus zinc plus 2. And that gives you a cell potential of plus 0.3 volts plus 0.76 volts, which is where we got the 1.1 volts. All right, so that is how you determine standard cell potentials. All right, so let me see how well you've grasped this. Oh, the other thing is that if the potential is greater than 0, if it's positive, that tells you that the reaction is spontaneous as it's written, and if it's negative, that means it's spontaneous in the other direction. All right, so here's our example. You have a cell that has the following components. You've got zinc and zinc nitrate and manganese nitrate. And you're going to describe the cell in shorthand notation, write a balanced equation, and tell me the standard cell potential. So this is this question hits all the points we've talked about so far. All right, so look at the two. So here you've got zinc and zinc plus 2. Here you've got manganese and manganese plus 2. Again, how can you tell it's plus 2? The nitrates. So here we've got the zinc reduction potential at negative 0.76. And here we have the manganese potential at negative 1.18 volts. Now, remember, the rule is that the most positive one stays. And negative 0.76 is still more positive than 1.18. So this reaction occurs as is. This one, the manganese one, is one that gets flipped and becomes the oxidation half reaction. So we could write our cell shorthand like this. The oxidation is manganese to manganese 2. There's a salt bridge. The reduction is zinc to zinc plus 2 to zinc metal. The chemical equation would be manganese reacting with zinc plus 2, giving you zinc and manganese plus 2. And what would the cell potential be? Again, so this one stays as it is. This one gets flipped, which means we have negative 0.76 volts plus a positive 1.18 volts, which gives us a total cell potential of standard cell potential of 0.42 volts. And again, this is about what you would get on an exam, and I would, of course, give you this information as you need it. I'm not going to have you, memorize any of these tables. All right, one more example just to see. This is a little more complicated. So I have a cell that I know that the anode is nickel being oxidized to nickel plus 2. And I also know the standard cell potential is 0.12 volts. So which one of these is the, which metal listed among here is the cathode constructed from? And so this one, pen out here. So let's work this out. So you know that the oxidation half react potential plus the standard reduction potential equals the standard cell potential. And we know that the oxidation, the anode, is 0.12 volts, and that's nickel right there. So that what I did here is actually incorrect. That's the cell potential overall. So I know that the oxidation, I know that's nickel, and that is, so the reduction potential for nickel is negative 0.25 volts. But I know that the nickel is actually being oxidized, so it's going to be positive 0.25 volts. What I don't know is the reduction potential, and I know that the whole thing is positive 0.12 volts. both volts. So let's just figure out what our reduction potential is. So X here is going to be positive 0.012 volts minus 0.25 volts, which, if my math is right, is a negative 0.13 volts. Be careful with the signs here, and you look for something that hopefully matches. So that would tell us that the cathode is constructed of lead. All right, and that is standard cell potentials.